Well, kids, here we are, Tuesday, March 31st. Digital Learning Day, I don't know, 8, something like that. Yesterday, we quickly went over the jet stream, and we also went over land breeze and sea breeze. As promised, today is a review of the entire chapter. So I'm going to go through this page by page, and I'm going to touch on just the important things that I really need you to understand about the atmosphere. All right. Once I get through this, I'll try to keep it to 10 minutes because your time is valuable. Once I get through this, there will be a larger quiz for you to do. Somewhere in the neighborhood of 20 questions that will encompass the entire chapter. So pay attention, excuse me, to this review, and then also follow along with me in the digital version of the book and use those resources when you're taking the quiz. So if I can stop, with the tickle in my throat, we're going to get going. So here we go. To start off, the importance of the Earth's atmosphere, bottom line is we can survive in this atmosphere and this atmosphere alone. We have evolved for this atmosphere to work for us. Changes in the makeup of that atmosphere may directly impact our ability to thrive here, as well as other plants and animals. What's in the atmosphere? Lots of gases. The main thing, nitrogen. It's the number one gas in the atmosphere, 78%. Oxygen, 21%. The rest are just trace amounts, except for water vapor, which varies between 1% to 3%, depending upon if you're in a warm, moist climate or a cool, dry climate. So we've got lots of gases. There are also solids in the atmosphere. The three that we talked about most were dust, pollen, and salt. There are others as well, but those are the three big ones. Remember, when you look at a ray of sunshine, which we haven't seen for like a week, but when you see a ray of sunshine coming through the window and look off to the side, you can see stuff floating around through that ray of sunshine. Typically, that's what it's going to be. There are also things like skin cells and those kinds of things as well. So we got lots of gases, lots of solids, and then, of course, there are also some liquids in the atmosphere as well. We have liquid water, and we also have other things, sulfur in particular, that mixes in the atmosphere and comes down as acid rain. So the atmosphere is made of solids, liquids, and gases. We then went through the layers of the atmosphere. There are 5 of them. They're on this page. The troposphere is the layer that we live in. Goes up about 10 kilometers, maybe 6 miles or so. Then we've got the stratosphere, the mesosphere, thermosphere, and the exosphere. When we went through these, we had talked about kind of what are some things in each of those layers. We know where the jets fly and where meteor trails might be found, and the space shuttle, when that was flying, where that's at. Most important in this picture is the ozone layer, which we'll touch on here again in a minute, which is in the stratosphere. All right, so remember those 5 layers. The ionosphere, not all that important for us to remember right now. Atmospheric pressure. On the drawing that you did for me, you showed that the atmospheric pressure is highest at the Earth's surface. It's like this 65-mile thick layer of gases pressing down on us at the Earth's surface. So pressure is highest at the surface, and it gets less and less and less as you go up, 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 and into space. All right. Temperatures in the atmospheric layers vary greatly. In the troposphere, down here where we live, the higher you go up, the colder it gets. In the stratosphere, it evens out right here, mostly due to the ozone layer being there. Then it gets warmer again. Then it gets colder in the mesosphere, and very little bit into the thermosphere gets the coldest, and then boom, temperatures off the charts. Here's the deal about that. Temperature is nothing more than a measure of how fast the molecules of something are moving. The faster they're moving, the higher the temperature. Up here, there are so few molecules. Remember that most of the gases are down here. They're piled up on us down here at the surface, so there's less and less and less. There's so few molecules up here that the sunlight that does hit them makes them go crazy. They move super fast, and it's very hot in the sunlight. When they're not in the sunlight, they're hardly moving at all, and so they're extremely cold. All right, so that's why we get that wild swing of temperatures up as we get closer to space and in space. The ozone layer, hugely important. It protects us from ultraviolet radiation from the sun. We then talked about how humans unknowingly were destroying the ozone layer using CFCs, or chlorofluorocarbons, that were found in aerosol cans and refrigerants, those kinds of things. Fortunately, we figured it out. We stopped using CFCs. Here's a picture of that damage that we did to the ozone layer, the ozone hole. And fortunately, we figured it out, and it is getting better. All right. So that was section 1. Section 2, heat transfer. The main thing here is that the great majority of the energy that is used here on planet Earth comes from the sun, and that really only about 50% of the sun's energy that's pointed towards Earth actually gets down here to the surface and is usable here at the surface. The clouds reflect it, the atmosphere reflects it, the atmosphere absorbs some of it, and some of it, when it hits certain parts of the Earth's surface, are actually reflected back as well, especially ice. Ice is a big reflector of solar energy. So only 50% of it gets down here to the surface where we can use it. Then we went into the 3 ways that we talked about heat being transferred from one thing to another. And those 3 ways are radiation, conduction, and convection. Radiation is energy moving through rays and waves. We talked about the sun being an example of that heat energy travels through rays and get to us here on the surface when we're laying by the pool. It also works if you put your hand over a burner, not too close, you don't want to get burned. It also works when you're sitting next to a campfire. So that's radiation, rays and waves. The second is conduction, and conduction is when molecules bump into one another. The hot thing touches something else, all right? When our finger touches the hot part of the stove, that's conduction. Or when the pan touches the hot element on the stove, it's warming through conduction. And then the last one was convection, a little bit more tricky. Transfer of heat by the flow of material. How I describe it is hot stuff rises, cold stuff sinks. So hot air rises, it then shares that heat energy with cooler air above it. All right. So those are the 3 types of heat transfer. Very briefly, we touched on the water cycle. And the main parts of that, we have the sun's energy causing evaporation of liquid water where it turns into a gas. It rises and cools off where it condenses and makes liquid again. Eventually, those clouds get enough water in them and the drops get big enough that it falls back to the earth as precipitation, which can be rain, snow, sleet, or hail. And then it ends up running off into the lakes and streams and eventually back into the ocean. So that's the water cycle. That should be a review for you. All right. Lastly, section 3, air movement with wind. We talked about the uneven heating of the Earth's surface. Near the poles, the sun's energy is not as powerful because it's spread out over a much larger area because of the curve of the Earth. Near the equator, that sunlight, that energy is more direct and more focused, and so that's why we get warmer temperatures near the equator, cooler temperatures near the poles. When that happens, it creates differences in pressure. Cold air sinks. So this air sinks to the surface, which creates higher pressure. Here, where the air is rising, there's less pressure. And so we have low pressure areas. And wind always moves from areas of higher pressure to areas of lower pressure. Next, we talked about the Coriolis effect, which is basically the rotation of the Earth. The spin of the Earth causes the air to turn sideways, either right in the northern hemisphere or to the left in the southern hemisphere. Did anybody do the research on the toilet bowl water? Is it true? Does it go, opposite directions in the northern hemisphere and the southern hemisphere? The internet will know. It may also give you some bad information. All right. Lastly here, not quite lastly, but getting pretty close to the end, we have the major air or wind patterns on planet Earth, the polar easterlies, the westerlies, trade winds, and the doldrums. The trade winds were important for trade when people were cruising around in these things right here, in these sailing ships. We don't want to get in the doldrums. Lots of hot, warm air rising, and that doesn't blow these sails very easily. All right, so those are the major wind patterns on planet Earth. And then we wrapped all that up with the jet stream. The jet stream, a couple of important things about the jet stream. It separates large masses of air. In this case, for us near Wisconsin, we've got cold, dry air to the north of us because Canada is colder and drier. And we have warm, moist air down here to the south. And the jet stream keeps them separated. Wherever the jet stream happens to be in relation to Wisconsin determines what our air is going to be here in Wisconsin. If the jet stream is below us, we get the cold air. If the jet stream is above us, then we get the warm air from the south. All right. The other thing about the jet stream, it blows mostly from west to east, and it allows airplane travel to be quicker and more efficient when they go from west to east, as opposed to flying against the wind east to west. And then the last of the last, sea breezes and land breezes. Land does not hold its temperatures nearly as well as water does. In the daytime, as you can see along the coast here, in the daytime the land heats up quicker than the water does. So it has warm air above it. That warm air rises, which brings in a cool breeze off of the sea. Therefore, that is called a sea breeze. Same location, this time at night, the land cools off more quickly than the water does. So now the water is warmer than the land. So the air above the water rises, the air on the land sinks, and it moves out to sea. So in this case, we have a land breeze. And that, folks, is it for the atmosphere. So the last thing you need to do is you need to go through, you need to use these resources, use my lessons to take this, not quite done with it yet, might be 20 to 25 question end of the unit assessment on the atmosphere. So use your resources, use me, Google Hangouts, Google Meets, email, something. Get a hold of me if you're struggling with this stuff so that I can help you. All right. With that said, that's going to wrap it up for the day. When we have this all finished up, hopefully by the end of the day tomorrow, we're going to move on to weather. So until then, I'll see you next time.